Okay. Hi everyone. I'm Longsen Lü. I'm going to talk about the geometric algorithm for contrastive PCA in high dimension. And my co-authors are Shaoxuan Wang. He is assistant professor from National Central University, and also Su Yun Huang. She is my advisor, and she is she is from Academia Sinica. Okay, this is the outline for today's talking. And first of all, we'll introduce the concept of contrastive PCA. And what is contrastive PCA? And suppose we want to analyze a given data, and we know the data contains some uninteresting information. And so contrastive PCA aims to eliminating the uninteresting information from the given data set, and make the data clear and easier to be analyzed. As you can see later, the contrastive PCA is equivalent to conduct a eigenvalue decomposition of a certain symmetry metric. But in the high dimensional setting, as you will see, the eigenvalue decomposition is impossible and impractical. So we want to convert the eigenvalue decomposition to a maximization problem in Stiefel manifold, and because we want to solve an optimization problem, so we use a gradient ascent line search algorithm and on the Stiefel manifold, and we will generate a sequence, and we believe the sequence will converge to the solution of our maximization problem. And we will show the convergent property later, and also we will provide the numerical studies that is emits the data set mixed with Grace image and chase X-ray images. Okay, this is the outline for today's talking. So let's introduce our problem setting. Okay, let's introduce the contrastive PCA first. Suppose we are given a target data set, and we are interested in the target data set, but we know the target data set contains some uninteresting information from background data set. So we hope to find the subspace that enrich the variance of target data set relative to the background data set. Okay. And as you can see the figure here, the blue represent the target data set, and the gray dot represent the background data set. And we hope to find the projection that somehow minimize the information from the background data set. And we can see there are two lines here. The red line represents the projection conducted by PCA, and the green line represents the projection by contrastive PCA. And you can see that in this case, the CPCA performs better than PCA because PCA cannot effectively eliminate the information from background data set. And we know the background data sets contains some uninteresting information. So, okay, now we introduce the mathematical representation of contrastive PCA. Suppose XI denotes the target data set, and the YI denotes the background data set. And the sample size of target data set is n, and the sample size of YI is background data set is m. The contrastive PCA is to find the leading eigenvectors of sigma alpha, where sigma alpha is equal to covariance of X minus alpha covariance of Y. Here alpha is the contrast parameter. Okay, if alpha is equal to 0, then the CPCA reduced to PCA method. And as you can see, as alpha increase, alpha is a non-negative variable. As alpha increase, and then the directions with smaller background variance become more important. And in the limiting case that alpha equal to infinity, then any direction not in the null space of background dataset receives an infinite penalty. So in this case, the contrastive PCA is to project the target dataset onto the null space of background dataset, and then conduct the PCA. Then we'll get the contrastive PCA in this limiting case. So this is target dataset. This is the background dataset. The contrastive PCA is to solve the eigenvalue decomposition of this matrix. So here show the example. And this is the example of handwriting ethnic image, and also the mix with Grace image. So our target dataset is a mixture of handwriting image and the Grace image. And we know the Grace image is uninteresting. So we hope to eliminate the information from Grace image. So our background dataset is a collection of Grace image. Okay, here we show here we show the reconstruction by PCA and the contrastive PCA here. So as you can see, this is the construction by PCA, and this is the reconstruction by CPCA, and you can see the CPCA performs better than PCA because CPCA successfully eliminate the information of Grace image. Okay, that's the introduction of contrastive PCA. But in our case, we want to apply our method to the high dimensional data. So the contrastive PCA is to solve the eigenvalue decomposition of sigma alpha. It is impossible because sigma alpha is large, it's of big size. So we have to convert this equation to a maximization problem, because size of sigma alpha is extremely large in high dimensional setting. So it is impossible to solve the eigenvalue decomposition directly. So we convert this problem to the maximization problem here. Here U star is the maximizer that maximizes F alpha. F alpha is equal to this formula, 1/2 trace UT sigma alpha U, and the U is constrained on stable manifold. That is U is equal to identity. So this is the definition of stable manifold, and we want to find the maximizer on stable manifold U star that maximize the F alpha. F alpha is our target function. It's our objective function. And this is the definition of tangent space of stable manifold. And Z is in the tangent space if and only if Z T U plus UTZ equal to 0. That is equivalent to Z, that is ZTU is skew symmetric. So with this knowledge, and let's introduce our iteration process. Our iteration is a line search gradient ascent method. With a given initial point on the stable manifold, our algorithm will generate a sequence UK in a stable manifold, and we believe if our initial condition is good enough, our initial point U0 is good enough, then UK transpose will approach to U star transpose. That is, the span of UK will converge to the span of U star. in each iteration, suppose we are given a UK and we want to calculate the UK plus 1. And first we calculate the projected gradient of f alpha, and then we derive the curve via Cayley retracement mapping. And with this curve, we determine the step size that move the UK to the UK plus 1. So this is the diagram which showing our 3 steps in our iteration. The first step is to calculate the projected gradient. Because the gradient of f alpha is not in the tangent space, so we have to project the gradient onto the tangent space to form the green arrow here. And with this projected gradient, we use the Cayley retracement mapping to generate a curve that takes the current point with velocity equal to this green arrow. With this curve, I will introduce the Armini-Hall algorithm to choose the step size, which moves the current point to the next point. So this is a diagram showing our 3 steps in each iteration. So at the beginning, we observe that our gradient f alpha is equal to sigma alpha u. And recall our f alpha is equal to 1/2 trace ut sigma alpha u. So the gradient is equal to sigma alpha u, but we know that sigma alpha u is not in the tangent space because we multiply the ut on the left. It is not skew symmetric, so it is not in the tangent space. So we have to project our gradient f alpha u onto the tangent space, but the projection depends on the metric structure. So here we define the gamma metric. Here the gamma metric is if z1 and z2 are tangent vectors, then z1 inner product with z2 gamma is equal to this equation. Trace z1 transpose identity minus gamma uut z2. So we give some remarks here. If gamma equal to 0, then it is the Euclidean matrix. If gamma equal to 1/2, then it is the canonical matrix. With this gamma matrix, the gamma projection is given by this formula. Suppose we are given P by R arbitrary G matrix, then the projection of G is equal to this formula. We can see some remarks here. If gamma equal to 0, then the projection is equal to this formula. And if gamma equal to 1/2, then projection is equal to G minus U G transpose U. But we give a proposition here. Suppose we substitute G by gradient f alpha, that is equal G. Suppose we substitute G by sigma alpha u, then the projected gradient is equal to this formula, which is independent of gamma. So, which means it is the same for all gamma value. So we use the Euclidean measure that is gamma equal to 0 in our following discussion. Okay, our next step is to derive the curve on the stable manifold. We derive the curve by Cayley retracement mapping. What is Cayley retracement mapping? Cayley retracement mapping is a retraction, which means it maps from the tangent space to the stable manifold. In spatial arc, the Cayley retracement mapping is defined by this equation. So C of tau z is equal z is a tangent vector in the tangent space, and the Cu of tau z is equal to this formula, where W is equal to this formula, capital pi U of z ut minus U capital pi U z of t. Where here capital pi U of z is equal to this formula, and then with the Cayley retracement mapping, this curve will satisfy satisfy these 3 conditions. The first, that this curve is in the stable manifold, and for the second, this curve is has the initial point equal to u, and this curve, the derivative of this curve is equal to z. But now we have the Cayley retracement mapping is equal to this formula, but it contains the inverse of a P by P matrix. Here our P is very large. So it is not computable. So we want to use, we have to transform this equation to another equation that is computable. So by the Shulman-Morrison-Woodbury identity, we can see that this matrix, the inverse of this matrix is equal. The inverse of this matrix is equal to this equation, and this equation just only contain the inverse of 2R by 2R matrix, but our 2R by 2R matrix is small size, so this is computable. And the Cayley distribution curve can be expressed as this formula, and you can see this formula just only contain the inverse of 2R by 2R matrix. It is small size, so this expression is easy to be computed. I also give a proposition that this matrix is invertible. So for any tau, this matrix is invertible for all tau, for all real number tau. The Cayley distribution curve is well defined for any tau. So this is the Cayley distribution mapping. Our next step is to determine the step size, and we use the Arming-Hall condition to determine the step size. The Arming-Hall condition is that given initial tau 0 and the beta 1, beta 2 belong in 0 and 1, the Arming-Hall condition is given by this inequality. Here, norm F denotes the Frobenius norm, and the beta 1 m tau 0 represents our step size here, and we hope to find the small integer m that satisfy this condition, and we want to find the MA that is the smallest integer that satisfy the Arming-Hall condition, and we denote tau A is equal to this formula, and tau A is the Arming-Hall step size. We hope to find the tau A. So by this inequality, you can see as our m goes to infinity, that means this part will equal to the sectional derivative of f alpha along the projective gradient. So this, as m goes to infinity, then this part is equal to this term. So, and because our beta 2 is smaller than 1, so as m large enough, then the Arming-Hall condition holds. But on the other hand, for n small enough or negatively large enough, we can see the Arming-Hall condition will not be satisfied, because this function, suppose this term is equal to this term, and we can see this term is linearly increasing as a function of tau. But this term is, our arbitrary function is defined on the Stifel manifold, and the Stifel manifold is compact manifold. So this term is less than the f alpha of u star, because u star maximizes f alpha. So as we can see, for tau large enough, then the Arming-Hall condition will not satisfy. That means for m negatively large enough, the Arming-Hall condition is not satisfied. So we have a proposition here. MA exists. That is, we also can find the smallest integer that satisfies the Arming-Hall condition. So this is the pseudocode for Arming-Hall algorithm for step size selection. Suppose we have given an objective function f alpha u, and we input current point uc and the initial step size tau 0 and the tuning parameter beta 1 and beta 2. Then when we do these 3 steps, first is to calculate the gradient, and the second is to calculate the projective gradient, and the third step is to calculate the Arming-Hall value A. If Arming-Hall value A is positive, which means we have to straighten the step size or elongate the step size. So we have to update our tau 0 by tau 0 over beta 1, and update our armyhole value A, and until our armyhole value A is negative. On the other hand, if A is negative, then we have to shorten the step size. So by this algorithm, the output is tau A, is the armyhole step size to calculate the fitable step size. So this is the armyhole algorithm for step size selection. And this is our main algorithm. Suppose we have given objective function f alpha, and the input is u0 and the initial step size tau 0 and the tuning parameters beta 1 and beta 2. Then we perform these 5 steps. First is to calculate the gradient, and the second is to calculate the projected gradient, and then calculate the armyhole step size by the algorithm above. And we update the step size by tau A, and update the current point by this equation. Then we get the U output, which we believe U output is equal to U star. That maximize our objective function f alpha. So let's go on. Suppose we have a definition that U is a stationary point if the projected gradient of f alpha of U is equal to 0. And we give a lemma here. U is a stationary point if and only if span of U is a span of R eigenvectors of sigma alpha. That is, span of U is equal to the span of eigenvector of sigma alpha. But we hope to find the leading eigenvectors of sigma alpha. That is span of U star. And we give some remarks here. The first is that if US is a stationary point, then US Q is also a stationary point for any orthogonal Q, which means the stationary point is not isolated. It's a region on the stable manifold. And suppose US is a stationary point, then f of US is equal to the sum of the corresponding eigenvalues. And by these observations, two remarks, and our algorithm aims to estimate a basis of eigenspace. So we give the two theorems here. The first theorem you can refer the first theorem by this book. Suppose UK is a sequence on a stable manifold generated by our algorithm. Then there exists a convergent subsequence UKJ to a stable manifold. Because the stable manifold is a compact set in the Euclidean space. So any sequence have a convergent subsequence. And the convergent subsequence have a limiting point. Every limiting point of a convergent subsequence is a stationary point. Also, we have that, and our UK is a sequence generated by our algorithm. Then the projected gradient of UK will converge to 0. So we have our main theorem here. Suppose U star is our maximizer, and there exists a neighborhood of U star transpose in the P by P, such that if our initial point is close to the U star transpose, that is, our initial point is satisfied U0 transpose is in this neighborhood, then UK transpose will converge to U star transpose. So, which means if we have a initial point that is good enough, then our algorithm will converge. Then UK is generated by our algorithm, and the UK will converge. The span of UK will converge to the span of U star. So this is our convergence theory. Okay, let's show the numerical example here. We provide two numerical examples. The first is MNIST data set mixed with Grace image, and the second is the chase X-ray image. Okay, this is the MNIST data set. Okay, and this is the data description. For the background data set, we have 30 images of Grace. and each image is size 28 by 28. And our target data set is a mixture with Grace image and handwriting image. This is our target data set. This is our target data, and this is our background data set. And we conduct our data analysis, and our contrastive parameter alpha is equal to 1, and we derive a 50-dimensional subspace. That is, our P is equal to 784, and our R is equal to 50. Because it is not high dimensional, so first we can solve the eigenvector directly. This is denoted by UCPCA, and we can also use our algorithm to derive the U hat CPCA. That U CPCA is approximated by our U hat CPCA, and as you can see, this is the reconstruction by UCPCA. This is the reconstruction by our algorithm. And as you can see, we perform the method iteration is equal to 50, and we can see the objective function value is increasing. So, and we also can derive the similarity. Here, similarity. The definition of similarity is equal to a singular value decomposition of U of this formula. And we can see this is used to measure how close between this span and this span by our algorithm. Because you can see that this is Frobenius norm of this projection metric and also this projection metric. And this is the difference of Frobenius norm of projection metric, and this term is equal to 2R product by 1 minus mean of S squared. So, which means if our mean of S squared is equal to 1, which implies these two projection metrics makes no difference. That is, span of UCPCA is equal to span of U hat CPCA. And in our case, our mean of similarity is equal to this number. This is very close to 1. So it's in the low dimensional case, but in the high dimensional case, and we repeat the original image to form the 3x3 extension to the size of 84 by 84. The original is 28 by 28, and we repeat to 84 by 84. This is the 3x3 extension of our original handwriting images. So, and this is 84 by 84 for each repetition, and we use an handwriting image, but different Grace images. So this is 84 by 84, and as you can see, we also conduct our contrastive PCA, and with our contrast parameter alpha is equal to 1, and we derive a 50-dimensional subspace, and we also denote the eigenvectors of sigma alpha, and the U hat CPCA is generated by our algorithm. Okay, let's see the result. And this is our objective function value. And you can see in each for us, it is increasing in our iteration. And this is reconstruction by our method. And this is the similarity. So in this case, similarity, the mean of similarity is also very close to 1. And this is the trace X-ray data set. A trace X-ray is this is a classification of diagnosis of pediatric pneumonia using chest X-ray image. The left-hand side is patient individual, the image of patient individual, and the right-hand side is healthy individual. And this is the data description here. So in our case, our P is equal to 224 by 224. So it is 50,176. Our P is equal to this number. And because we want to derive a two-dimensional subspace, so in this case our R is equal to 2, and we conduct our algorithm by alpha equal to 1/2. So you can see the comparison between this is the projection by the testing data set, and the red dot represent the patient individual, and the blue is represent the healthy individual, and this is the projection by PCA on the testing data set, and this is the projection by our algorithm used by CPCA with alpha equal to 1/2, and you can see our projection performs better than PCA in this case, because we can successfully separate the patient individual and the healthy individual. Okay, and this is my reference, and okay, this is my talk today.